In class activity 18B, spheres and rates of change. When a sound is emitted, it creates a sound wave that spreads quickly outward from the point of origin, similar to an expanding sphere. As the radius of the sphere increases, its volume increases as well. The radius increases at a rate equivalent to the speed of sound, approximately 1,126 feet per second. 1. Can this speed be used to determine how fast the volume is increasing? And the answer, let me turn the marker on first. There we go. Well, the answer is yes. So let me put a yes here. In class activity 18A, the rate of change of the area of a circle depended on how fast the radius was increasing and the size of the circle. The same might be true here. The volume may not increase at a constant rate. Let's go to the objectives. Objectives for the activity: you will understand the volume of a sphere whose radius is changing at a constant rate with respect to time will not change at a constant rate. You will be able to use the relationship between volume and radius of a sphere to determine the relationship between the rates of change. You will be able to compute rates of change. Next screen. Spheres of increasing radii can be used to model sound waves. The radii of these spheres increase at the speed of sound, which is approximately 1,126 feet per second, in air that's 66 degrees Fahrenheit. The volume of a sphere is 4/3 pi r cubed. Let V1 be the volume enclosed by a sound wave of radius R1, and V2 be the volume enclosed by a sound wave of radius R2. Also, let delta V represent the difference between the two volumes, and delta R be the difference between the two radii. 2. Find the formula that relates the change in volume of a sphere enclosed by the sound wave to the change in radius. You'll need to factor a difference of cubes to accomplish this, and it's listed right here for us, in case you forgot. And then let's do this. I'm going to take V, call it V sub 2. Whoops, V sub 2. That should be minus V1 equal to 4/3 pi r cubed, and that's R2. So R sub 2 cubed minus 4/3 pi R1 cubed. So then we have V2 minus V1 still equals, if we factor out the terms common, we get 4/3 pi, and then parentheses, that's R2 cubed minus R1 cubed. And then we still have V2 minus V1 on the left side. And then we get 4/3 pi, parenthesis, R2 squared plus R2 R1 plus R1 squared times R2 minus R1. Let me just scroll that up a bit. And then we can change the notation from the V2 minus V1 and write delta V, and that's equal to 4/3 pi times R2 squared plus R2 times R1 plus R1 squared, and the parentheses, and then the R2 minus R1, we can change that notation and use the delta R. Part 3, use your answer from question 2 to determine a formula for the average rate of change of volume, delta V over delta T, in terms of the rate of change of the radius, delta R over delta T. Let's write this delta V over delta T, and we could write 4/3 pi R2 squared plus R2 R1 plus R1 squared. And then we could write here delta R over delta T. 4. So what is the average rate of change for the volume contained in the sound wave as the radius increases from 18 to 20 feet? A 2-foot increase. Write a sentence explaining your answer. Use appropriate units in your explanation. So let's see, I'm going to scroll down a bit. And if we plug in all the numbers here, we're going to get a value approximately 770.3 cubic feet per second. So we can see here that as the wave's radius increases, would be from, what does it say, 18 to 20 feet, comma, the volume contained by it is increasing an average rate of, and this is just the same number that's above 5,112,770.3, and that would be cubic feet per second. Number 5, what would the volume increase by the same amount? What would the volume increase by the same amount if the radius changed from 0 to 2 feet? Again, a 2-foot increase. And it's not going to change by the same amount. So we're going to put a no here. And we could write delta V over delta T is equal to 4/3 pi times 2 squared plus 2 times 0 plus 0 squared times 1126. And this is going to be approximately 18,866.3, and that's cubic feet per second. So as the wave's radius increases from 0 to 2 feet, the volume contained by its increasing by it is increasing at an average rate of 18,866.3 cubic feet per second. Number 6, weather balloons are nearly spherical in shape. A weather balloon is inflated at a constant rate of 2,500 cubic inches per second. Using the relationship between the average rate of change in volume and the average rate of change in radius for a sphere, find the average rate of change for the radius as it increases from 10 inches to 15 inches. Okay. So we know from question 5, we have delta V over delta T is equal to 4/3 pi, or 2, let's make that look like a 2, R2 squared plus R2 times R1 plus R sub 1 squared, and that's delta R over delta T. Here, we know the average rate of change for the balloon is, okay, so the average rate of change for the balloon, let me put that here. The average balloon, there it goes, balloon is delta V over delta T. It's 2,500 cubic feet per second. And let's make some more room here. Solving for delta R, over delta t is, let's see, delta r over delta t is equal to delta v over delta t over 4/3 pi r squared plus r times r 0 plus r sub 0 squared. Then continuing here, well, the numerator is just going to be 2,500. We do that. And then we get 4/3 pi. We get 15 squared plus 15 times 10 plus 10 squared. And this is going to be pretty close to 1.26 inches per second. Well, that's the end of this video. Thank you.